All right, so yeah, so the first problem, convert what is the number 10 in 6-bit 2's complement binary. So the thing is, this is not asking about the 2's complement of 10. This is asking what 10 is in 2's complement. That is 10 in 2's complement. So that's something very important to distinguish, is there's a difference between what the 2's complement of a number is and whether or not you're just working with 2's complement binary. Because this is how you write 10 in 6-bit 2's complement binary. For the second question, it's what is the 2's complement of 4 in 6-bit 2's complement binary. So that means we can start with the number 4, make that 6 bits. Now it says take the 2's complement of that. So now we go ahead and take the 2's complement. Invert, add 1, and we get that this here is the 2's complement of 4 in 6-bit 2's complement binary, or negative 4, right? So any quick questions on these are questions right on the bulletin board on the lecture canvas page. Okay, any quick questions on this? And please, like, if you have a question, start typing them out immediately when you have them. I'll see it when 2's complement binary means 2's complement binary. It's like this right here is negative 4 in 6-bit 2's complement binary. That's 10. So all that means is just 6-bit 2's complement binary is a way to represent a way that numbers are represented in in binary. So that this is 10. This would be 3. This would be negative 1. Right? It's just a way that all of these 6-bit binary numbers are assigned. 2's complement of something is the negative of something. Is there a question? I definitely want to try to keep going because these are some of the shorter ones. If your question is, would you end up with the same thing? Yes, technically, what you write would be the same thing. Okay, so moving on to the next question. So then implement the following expression using only NOR gates. And for this, I'm not going to bother actually drawing it out, but I'm going to just convert the expression itself into an expression with NORs. So for NORs, I'm going to want to do something like A plus B not, right? And I want to express everything in terms of doing this operation here. And that's just going to involve applying De Morgan's law a whole bunch. So we're starting off with A, B, or not B, C. Okay, well, I can't do and, so I need to use De Morgan's law here. So A, B, that's A and B, right? A and B. Well, that's the same thing as not A or not B. Right? So now I do have a NOR, right? This OR here with the not, that's a NOR. But now I have not gates here, but I want NORs. So here I can actually just do not A or A to get not A. So this is going to be equal to not A or A. Please, if you have any sort of comments, post them in the Lab 81 so I don't have to search around in Discord. Not B or B. So A and B is equal to this massive thing, which is only NORs. Then we have the second component, not BC. So here we can apply De Morgan's law. That's right. That's just NAND or not B and C. If I apply De Morgan's law, this is equal to not B or not C. And then you'd have to split this up. So again, B or B is equal to B. So we can just do this is equal to not B or B, or not C or C. And this is all using NOR gates except for this one OR right here. So that we would technically have to add an extra OR, or an extra not on the outside. So that, let's see, what would the easiest way to do that be? Well, let's just write it out. So far we have that everything is equal to not A, or not B or B, or not B or B, or not C or C. And ideally we want to make some of these, well, we want to make these ORs here or NORs. And so what we would be able to do, and I'm not going to write it out because this is big, I didn't really plan ahead what this answer would turn out to be, which is going to be massive, but essentially you can just put a double inversion here, right? So I would have not this, or, well, this again, not exactly the same stuff, and then all of that would be knotted again, right? So if I have A or B, right, and I want to represent that in NOR gates, what I'm going to have to do is not A or B, or not A or B. It's tedious, but yeah, but that's what we have to do with this long string here. So if I want to express this whole thing in terms of this, I'd have to do that whole crazy stuff. So yeah, I will probably be posting this on YouTube. It is being recorded, so that is definitely a possibility. Give me a second to respond to some things. All right. So can anyone not see my screen? You should definitely be saying so. Okay. Yeah. So yes. Yeah. Essentially, you'd have to come up with an equation, but you can be rest assured that the equation isn't going to be something massive and complicated. It's going to be something a little bit more simple. So you don't have to worry about it being too large. But yes, you might have to do something like this on the test. So it's essentially just know how De Morgan's law works, know how to be able to apply it to convert, so that you can maybe make everything out of NAND gates or NOR gates or something like that. Okay. Any last little questions on this? This is something that you probably just need to practice. You are not drawing it. That's what I just answered. You're going to be writing this equation using only NOR or NAND gates. Right, like if I was just doing AB here, the answer would be this. Because that's all NOR gates. Okay, then we have a truth table question. So this is the truth table here. Let me actually make that a little bit bigger. Which I cannot remember how to do. No, not that. Let's zoom in. Fine. There we go. Okay. So first thing, sum of products. So for sum of products, you want to look for everywhere there's a 1 in the table. And you want to come up with the minterms for those. So here, there's one gate that is going to be 1 only when A is 0, B is 0, and C is 1. And that gate is not A, not B, C. So whenever there's a 0, you put not whatever it is. Whenever it's a 1, you just put whatever that letter is. And you can see if you pass in 0, 0, 1, that's 1 and 1 and 1, which is 1. And this will be 0 every other time. Right? And so then we just do that for every single thing. And then or everything together. So we have that Q equals not A, not B, C, or not A, B, C, or A, not B, not C, or A, B, not C. Any questions on sum of products? All right. Moving on, we then have that we want to do a K-map on this. So we can go ahead and draw out the K-map. And this is definitely something that you're going to want to practice. You definitely don't want to mess up on a K-map if you have to do one. So it's 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Again, pay attention to the order of these, otherwise your K-map will not work. Then we maybe put A, B up there, see it here. Then we need to transfer everything over. So we have 0, 0, 1, that's right there. We have 0, 1, 1, 0, 1, 1. We have 1, 0, 0, 1, 0, 0, and 1, 1, 0. It's right there. So then we want to, and again, the rest would be 0, so I just leave them out. So then you want to circle in, you want to see how you can circle things. So we can start off with a circle of 8. It's not possible to circle 8 in a rectangle. Then go down to 4. It's not possible to circle 4 in a rectangle. Then you can go down to 2. You can see, let's say, for instance, this one can be circled with this one, and that's the only way that it can be circled. So this will be included in our answer. Then we go to one of the other ones that hasn't been circled. We can see that this one only has one other one it can be circled with, so we can go ahead and circle with it. And then everything's circled, so now we're done. Then we can come up with the minterms. So for minterms, you should not be doing Boolean algebra. Don't just like extract the individual terms and then simplify. That's extra work for no reason. This bubble right here is in these 2 columns in this row. If I look at just the columns, I can see A is always the same. So that means it's going to be in the answer. And it's not, because it's always 0. B changes, so we're going to leave it out. C is always 1, so we put it in the bubble. We put it for the term. Then we can go on to this next one. So that is this first row and these last 2 columns. Here we can see A is always the same. It's always 1. B changes, so we'll leave it out, and C is always 0, so that'll be not C. And so that means we have Q equals not A, C, or A, not C. Any questions on K-maps? All right, so now we want to implement this with a 2-variable mux. So we'll go ahead and start with the 2-variable mux. Keep in mind, 2-variable mux means there are 2 selector lines. S1, S0, for instance. We have our inputs, I0, I1, I2, and I3. And we just want to specify what each of these is. And like on a quiz, you'll literally just go I0 equals blah, I1 equals blah, I2 equals blah, and so on. So you don't need to draw this out. So here, I'll go ahead and choose A and B for my selector lines. So now, what happens when A and B are both 0? Well, that corresponds to these first 2 rows here. And we can see, if we look to the right-hand side of this, and we split this up here, we can see that Q is always equal to C. So that means we want to put a C here, so that this output here is Q. If we put a 0, 1 here, well, these 2 rows correspond to when A and B are 0 and 1. We can see Q is again always with whatever C is. So we put a C for I1. Then if we put 1 0 in, right, 1 0 will select I2 so that we know that we're putting something here for the output. And these two rows here correspond to when A and B are 1 0. And we can see here that Q is always exactly not C. So we can put a not C here. And then finally, when they're 1 1, we'll again have that Q is not C. So we can put that there. That would be it. So this would be the answer, at least one of the answers. There's a couple. So here again, just we would have S1 equals A, S2 equals B, I0 equals C, I1 equals C, and so on. That's just how you should write your answer. No need to draw anything out. Any questions on this? All right, so now we're moving on to FSM stuff. So first thing we're going to do with the FSM here is just figure out what sequences it detects. And specifically, this is a sequence detection FSM. Not all FSMs are sequence detectors. Most FSMs are not sequence detectors. So don't just assume that it detects some sequence of binary numbers. So here, something that I've seen people do is assume that whatever's in the state is what the previous inputs are, and that it's just whatever the state is followed by whatever the input is what the sequence it detects. That is not true. That the state is completely independent from what the input and output is. I mean, the state, what the state ends up being depends on the input and output, or really the input, but what state variable is used for Q2. Like if Q2 could either be 1 1, or it could be 0 1, or it could be 1 1 1 0 if you're using some weird state encoding. It can be literally anything. You can represent however you want. So it never doesn't mean that it's whatever was recently input. So what we need to do here is find what sort of sequence works. So let's say I want to see if the sequence 0 works. Does the sequence 0 work? No, because if I start in this state here and I take 0, the output's 0. Right? It should always work. It should always detect the sequence. So 0 is not a sequence detected. Is 1 a sequence detected? Well, no. Right here, if I look on this edge here, if I go from Q2 and I input a 1, it outputs a 0. So that means it wouldn't detect the sequence 1 every single time. Okay, well now let's go up to 2, 0 0. So if I start at Q1 and I input 0 0, well the second 0 that I go on outputs a 0. So it's not detecting 0 0. Is it detecting 0 1? 0 1. Well, that output is 0 on the second arrow, so that's not valid. And you know, you can start from it should work from no matter where you start. If you start at Q0 and you see 0 1, it should work. You start at Q1 and you see 0 1, it should work. No matter where you start, it should always work. In fact, it should always get you across the same exact line. So if I then do 1 0, if I start let's see here, no, here, where should I start? Well, so yeah, so let's say I start in Q2, so I go 1, right? That's an input of a 1. I go here, and then 0, I would output a 1. So maybe it detects 1 0. But if I go here and I go 1 0, that works as well. If I go here and I go 1 0, it also output, but it outputs on a different line. So that's not actually a valid output. So it has to output on the exact same arrow twice. So this isn't technically true. It does not detect 1 0. And then 1 1, we can easily see if we just go here, 1 1, that just outputs a 0, so it does not detect 1 1. So then we go up to 3, 0 0 0. Does that work? Well, you can be a little bit more intelligent about this. You know that you have to come across this arrow here, right? So we know that our code has to end up with a 0. Here, I should be able to start from anywhere. So I can just sort of backtrack by 2, and that should tell me like what one of the sequences is. So here, if I go backwards along this wire, here, along this arrow here, and then from Q2 I go backwards along this arrow, and then I go backwards along this arrow, you can see that if you play that in reverse, it's 0 1 0. So 0 1 0 is a potential candidate here. And again, if I go here and I go 0 1 0, it goes across this line here. If I go 0, 1, 0, it goes across this line. If I go 0, 1, 0, it goes across this line. If I go from here, 0, 1, 0, it goes across this line. So this is the sequence that is detected. So that's the sequence that is detected by this arrow here. Now for this one, we can again go backwards. So last thing is a 0. Then maybe we have a 1 before that. And then a 1 before that. So the other sequence would be 1, 1, 0. So I guess technically this does actually detect the sequence 1, 0 because it does so regardless of this or this. But we'll specify the length of the sequence that it detects because that's actually something that's somewhat important. But yeah, it detects 0, 1, 0 or 1, 1, 0. So sort of it's detecting 1, 0. But that's how you want to do it. You don't want to look at what the state actually is. You want to see about how things transition as you input something. And if you constantly get an output on a specific input, then that means it's getting detected. It's always going to be detected. No matter what state you're in, it'll be detected after that input. Any questions on this? All right. So now we want to do the next state table with a specific state encoding. And that state encoding is Q0 equals 0, 1, Q1 equals 1, 1, Q2 equals 0, 0, and Q3 equals 1, 0. So I'll go ahead and use C and N for my current and next state for some simplicity here. So I have my current state, C1, C0, my input X, then I have my next state, N1, N0, and then my output, C. Okay, so then I'm just going to fill this out, and then we'll see what everything corresponds to. I'm just sort of filling this out in binary so that it's easy to work through and not just some random ordering here. Okay, so these first two correspond to one state. That's the state 0, 0, which is Q2. So if I'm in state Q2 and I see an input of a 0, I'm going to go to Q1, which is state 1, 1, and I'm going to output a 1. So that was this arrow right here. Right? I'm in state Q2, which is 0, 0, and I input a 0, which is the thing on the left. I will output a 1, which I've covered up, but you output a 1, that's the stuff on the right, that's the Z, and then you go to state Q1, which is 1, 1. Fill that out. Then, if you're in state Q2 and you see a 1, you output a 0, go to state Q0, which is state 0, 1. Next one, 0, 1, that's Q0. So if you're in state Q0 and you see a 0, you're going to go to Q1, which is state 1, 1, and you're going to output a 1. If you're in state Q0 and you see a 1, you're going to output a 0 and go right back to state Q0. Then we have state 1, 0, which is Q3. If you're at Q3 and you see a 0, you output a 0, go back to Q3, which is 1, 0. If you're in Q3 and you see a 1, you're going to go to Q2, which is state 0, 0, and you're going to output a 0. Finally, if you're in state 1, 1, which is Q1, so if I'm in Q1 and I see a 0, I'm going to output a 0 and go to Q3, which is state 1, 0. And if I'm at Q1 and I see a 1, I'm going to go to Q2, which is 0, 0, and output a 0. So again, just going back over. So we have Q2, Q0, and Q3. If you're in Q2 and you see a 0, you go to Q1 with the output of 1. If you're in Q2 and you see a 1, you go to Q0 with an output of 0. If you're in Q0 and you see a 0, you go to Q1 and you output a 1. If you're in Q0 and you see a 1, you go back to Q0 and you output a 0. If you're in Q3 and you see a 0, you go back to Q3, output a 0. If you're in Q3, you see a 1, you go to Q2, which is 0, 0, and output a 0. And then finally, if you're in Q1 and you see a 0, you go to state Q3, which is 1, 0, and you output a 0. If you're in Q1, see a 1, you go to Q2, output a 0. Always make sure to check over your work, right? This table should just exactly represent this thing. So it should be relatively easy for you to run through here and make sure everything works out. Okay, so now we want to compute the tables for if we're going to implement this with the D latch versus SR latches. So to do that, we'll go ahead and just start with the D latches because they're a bit easier. So we'll have D1, D0. So for this, we want to ask ourselves the question, if we want a D latch to hold, like let's say we just focus on D0 right now, is if we want the D latch to hold this value and it's currently holding this value, what do we have to input into it? Well, here we just input it into it this value because that's how D latches work. You have to input into it what you want it to hold. So D0 is going to be the same as N0 and D1 is going to be the same as N1 because that's how you update a D latch. So then for SR latches, we'll have two sets here. We have S1R1, S0R0. These two, well, both the subscript 0 ones, those are for the N0 state or C0 state based off of whether it's current or next, and the ones are for the C1 and N1. So again, S1R1 is if it's holding what's in C1 and you want it to hold what's in N1, then what do you have to input into the SR latch to properly update it? And so for this, we want to create this little table. So if the current is this, the next is this, then we'll make S this and R this, right? So if we have all the possible different options, and we're going to use this lookup table, but fill it out first. So if the current is 0 and we want the next one to be 0, well, we can't set. If we set, it would become a 1, so this wouldn't work. So set has to be 0. But R here, well, if it's 0, it'll just stay the same, which is fine. That'll work. But if it's a 1, it'll set it to a 1. So that means we have 0 don't care. If it's currently holding a 0 and we want it to hold a 1, well, we have to set it to 1, right? S has to be 1, and R has to be then 0 because if R was 1, this would be invalid. So R has to be 0 here. S has to be 1 because we want it to set to 1. We can't maintain because that just wouldn't work, and we can't set to 0 because that wouldn't work. So here we want to do sort of the opposite of that. We want to set to a 0, which is 0, 1 here. If we maintain, that wouldn't work, so there's not going to be any don't cares here. And then finally, if it's currently holding a 1 and we want it to hold a 1, well, we could put 0, 0 here because that's a maintain, or we could put 1, 0 here because that would set it to a 1, which would also work, which means S is going to be don't care and R is going to be 0. And now we can just look up what the two values are and start filling out the table. So here we have 0 and 1. That'll be 1, 0 here. 0, 0, 0 star. 0, 1, 1, 0. 0, 0, 0 star. 1, 1 star 0. 1, 0, 0, 1. 1, 1 star 0. 1, 0, 0, 1. Then over here we have 0, 1, 1, 0. And again, just look up what's going on in this table. And sort of a little trick that you can use is when you see 0, 0, you put a star in the R column, right? Because 0 is reset. If you see 1, 1, you put a star in the S column because 1 is set, and you just leave the other 0. If you have two different things, just swap them. So 0, 1 becomes 1, 0, 1, 0 becomes 0, 1. And that's just a really easy way to do it quickly. So here I see 0, 1, so I'm just going to flip it around, 1, 0. Here I see 0, 0, so I'm going to put a star in the reset because it's zeros, and put a 0 on the other one. 1, 1, or sorry, that's the wrong column. 1 second. I was looking at the wrong thing. So here's 0, 1 becomes 1, 0, 0, 1 becomes 1, 0. Now I have 1, 1 here, so that's star 0. And then we have 1, 1 again, so that's star 0. Then I have 0, 0, 0 star, 0, 0, 0 star, 1, 0, 0, 1, 1, 0, and 0, 1. And then we would do K-maps from here. Let's see, how much time do we have? 20 minutes. So yeah, I don't think I'll be going. This is pretty much this. Then you would just do K-maps as normal, paying attention to don't cares if you need. Any last little questions before I move on? Okay. So now we'll go ahead and move on to the horizontal architecture questions. Or I guess the architecture questions in general. Okay. So to start, we have C equals left shift B and 1. Go to 12. So here, if I want to go ahead and draw out the data path, we're going to be taking B out here. We're going to take +1 out here. We're going to AND them together, take the result, left shift it. So after the shifter, it's going to get left shifted, and then we have new data out coming here, and it's going to go into C. Right, and that's pretty much all the data path. The rest is going to be implemented in here. So here we can see that AMX, the data is coming from the A latch, so AMX is going to be 0. Condition, we do have a go to 12, so that's going to be a jump always. ALU, we want to be doing bitwise AND, which is number 1. Shifter, we want to be doing a left shift, which is number 2. MBR is going to be 0 because we're not, and MAR because we're not actually putting anything into them. We're not reading, we're not writing in this instruction. We are putting something back into a register, so enable C is going to be 1. C here is going to be whatever we're writing to, which is the C register, so C is going to be 12. B is whatever we're reading onto the B bus, which is the +1 register, which is register number 6. A is going to be whatever we're reading onto the A bus, which is register B, which is register number 11. And then our address here is just the 12 in our go-to statement. Any questions on this? All right, and then we clear this out. And then we have the vertical architecture version of this question. So here we have, again, that's C equals left shift, B and 1, go to 12. So here we need to break this down into a sequence of steps that we can actually execute on the vertical architecture. So first we're going to have to do this B and 1, but we can't just do this B and 1 and overwrite either B or the +1 register. That would be bad. So we're going to first just start with C equals B. Then we can do C equals B and 1. Then we can do C equals left shift C. Then we can do ALU equals C, set the N and Z flags, or actually we don't need those because it's just a go-to statement. And then yes, we can just do the go-to. So go to 12. So this is the 4 statements here that we're going to need to do here. And then we want to implement them with the op R1 and R2 syntax. No. Or yeah, sorry. This right here should be C equals C and 1. Yes. So we have op R1 and R2. Our first operation, that is just x equals y, so that's op number 11. Then we have a bitwise AND, that's going to be op number 10. Then we have a left shift, which is op number 14. And then a go to, which is op number 6. Usually helpful to figure out what the ops are, make sure that each of these are actually executable in one operation. And then we can start filling out the registers. So for the most part, whatever's on the left-hand side is R1, whatever's on the right-hand side is R2. In this case, for this operation, this is what's on the right-hand side because C, it's like C and equals 1. So here the C register is register number 12, B register is number 11. So we're doing C equals B. Then we have C equals C and 1. So C goes here, the +1 goes here, and +1 is register number 6. Then we have C equals left shift C, and as you can notice, it's the syntax is X equals left shift Y. So here we're just going to put C for both because we want to take C, we want to left shift it, and then put it into C. And then we have go to 12, in which case we'd actually put 12 like across both registers. But in this case, we can also just say that R1 is 0 and R2 is 12, because 12 does in fact fit into a 4-bit number. Any questions on this? All right. So moving on to the second architecture question, which I will actually skip. I'll be skipping number 10 just for time's sake, but I will be going over number 11. Number 11 is really just saying do the first step of converting the instruction. We don't want the op R1, R2. We just want you to split it up into a sequence of instructions where each of them can be executed on the actual architecture. So the first thing we have is B equals C and B minus A. So we have to do this in a specific order. You need to use B in the operation in B minus A, so you don't want to overwrite B initially. So here I'm going to go ahead and do AC equals not A. Start getting whatever negative A is. So then AC equals AC plus 1. So that will make AC equal to negative A. Then we can go ahead and add that to B. So then I can do B equals B plus A, or AC. And the reason I can do overwrite B now is because I'm using B here. I'm adding that to it, and then I can AND it with C later. So then I can do the B equals B and C. So that will actually do the full operation, B equals C and B minus A. That can be done in this steps. Then we have to do the if Z go to 64. Technically here we do need to do the N and Z flags. So ALU equals B and Z. And then finally we can do the if C go to 64. And then if you're actually doing like implementing this as op R1, R2, you just convert each of these to op R1, R2. But if it just asks to give you, like, for you to give a sequence of instructions, don't worry about giving op R1, R2. In both, it's okay to do multiple, but you want to do the minimum. So if you can do it in one, do it in one. If you can do it in two, if it's not possible to do in one, you have to do it in two. What do you mean 2 rounds? I'm not sure what a round is. Cycle? Instructions? This is 6 instructions. I'm not sure what your question is. What do you mean you use 2 latches at a time? Like in the horizontal, you mean? In the vertical, this doesn't matter. Don't look at this. You look at this. Right? The way that these operations are ordered is based off of what this table tells you. The actual architecture does not matter at all for vertical. Like this could be completely structured in a completely different way, but if this is defined exactly the same way, then this is how you're going to use it. So you don't want to think A latch, B latch. You just want to think, okay, well, I want to do one of these operations. I can do one of these, so you set R1, R2 based off of that. Right, that's the whole point of the vertical architecture, is to not have to worry about what this is. Right? If you can program on this thing without actually knowing how it works, that's amazing. That's great. I mean that's really what you're doing when you're actually programming. You're taking a higher level language, you're programming in something that the computer can't natively understand, and then it gets compiled to something that the computer does. And that's essentially a very, very basic version of what this is doing. It's taking these high level instructions and then figuring them out using this opd code, figuring out what needs to happen. And that way you don't actually have to know how it works. You do have to know a little bit, like with how the NZ flags work, but that's relatively little in comparison to actually having to know how all the data moves along. Okay, so then I've got number 12. So 12 is a little pipelining question. So we have a sequence of instructions, and then we have 5 instructions here. The CPU it's just a normal CPU. There's not really anything interleaving, memory access. It's just about timings. So here we have 3 units, IF, MA, and EX. Doesn't matter what they do. Just gave them random names. And then we want to go ahead and figure out how this schedule will end up lining up. Actually, I'm going to make this a little bit smaller because it might end up being somewhat long. So okay, so now we have the IF unit, the MA unit, and the EX unit. So at the very start of the first cycle, we go ahead and start instruction number 1. So this is just saying instruction 1 will spend 1 cycle in IF and 2 cycles in the MA unit. And then 2 will spend 1 in every one. So we start off here, go here. So at the end of this cycle, 1 is done in the IF stage. So it'll go ahead and move on to the MA stage. And that means 2 can get started in the IF stage here. But 1 will spend an extra cycle in the MA stage. So it'll start here. 2 can't move on to the MA stage because of that. And we can't start instruction 3 because if we look at the units sequentially, we have the EX unit, MA unit, IF unit. First cycle, 1 is here. Second cycle, 1 moves to here and 2 starts here. Third cycle, nothing changes. 2 is still here. It's not actually using it. It's not doing anything in the, sorry, not, I did that backwards. This is IF. This is EX. So yeah, 2 is still in the IF unit. 1, because 1 is using the MA unit. 2 can't progress forward here. So we can't start 3 here. That would just not work. That it would mean that both 2 and 3 are sort of waiting in that unit. So we're going to wait until 1 is done and 2 can actually move forward to actually start number 3. Now on this cycle, 1 is done in the MA unit, so it'll move on, but it doesn't actually have to use anything else. So now instruction 1 is done. 2 will go ahead and move on to the next unit. And because now the IF unit is free, we can go ahead and start fetching 3. Next cycle, so now 1 moved out of the CPU, and remember these are sequential here. So 2 moved on to here, 3 is here. So next cycle, 2 is going to move up to here because that's the next cycle it needs. 3 also needs this unit. And so what it's going to do is we progress this forward. 2 moves on to here, and then 3 can just sit in here. It doesn't have to use the MA unit, but it can just sit in here as where it's temporarily being stored. So 3 is sort of in this unit here, which means we can actually start instruction number 4. So we can't start instruction number 3 here because 2 is still sitting in the unit, but we can start instruction 4 here because 3 can essentially just move on. It's not actually blocked by anything. It's not waiting to start something. It's just waiting to get to a unit that's much further along. So it still has a unit that it can sort of sit in while it's waiting, which is right here, but we don't actually write it down because it's not using it. So then this cycle is over. 2 is done. So 3 is going to go ahead and move up to the EX unit. So it'll go ahead and start here. 4 will go ahead and move on to the MA unit. And then we can go ahead and start fetching instruction 5 because nothing's in the IF unit. Now we have 3 is going to last 3 cycles in the EX stage. So 3 is going to stay right here. And then 4 is actually done. So it'll leave the pipeline. 5 then can go ahead and start moving on to this unit. All right, so 4 is done, so it leaves the pipeline. 5 moves on to the MA stage. And then if there was instruction 6, it could go ahead and get fetched here. But there isn't an instruction 6, so that would be done there. We go ahead another cycle. 3 is still in the EX stage. 5 here, because it spends 2 cycles in the MA stage, would stay in 5 in the MA stage. And then finally, after this cycle, 3 is going to be done. 5 could go ahead and move on to the EX stage. Any questions on this? All right, I'll go ahead and move on. If you have a question, go ahead and type it. I might be able to get to it, but yes, because it takes 2 cycles, and we wrote 3 in that same stage. 3 is in the EX stage for 3 whole cycles, so it's there for 3. Yeah, you like each of these blocks represents a cycle. So if it's in there for multiple cycles, it should be in multiple blocks. Number 13. So 13 is about interleaving. So here we have 6 instructions, and they use the following units. And here I'm just going to go ahead and specify this with the schedule. So we have one-way interleaving. And we have stages A, B, C, and D, where the A and C stages utilize the main memory. And here, everything is just going to spend 1 cycle in each of these units. So we begin with instruction 1. It's going to go ahead and start in the A unit. Right, so this is just saying instructions 1, 3, and 4 use all 4. Instruction 2 uses these 2 units, and so on. So 1 uses the A unit. That's the first cycle. We move on to the next cycle. The next unit A needs to use is the B unit. So it'll go ahead and move on to B. 2 here, we can go ahead and start in the A unit. And then we're done. We can go on to the next cycle. Then 1 is going to go ahead and move on to the C unit. So 1 moves on to the C unit. 2 would want to move on to the D unit. And we can't start instruction 3 because there would be an interleaving conflict here, right? Because then we'd be using A and C simultaneously. So we can't go ahead and start 3. And 2 is waiting to use the D unit. So then we can it'll move on to the next cycle. So 1 then just uses the D unit. 2 is still waiting to use on that, but it can be waiting in, let's say, the B or the C unit without using it. But now that we're free to go ahead and start instruction 3. And that's it for that. So we can move on to the next cycle. So now in the next cycle, 2 can finally move on to D. And 3 will move on to the B unit. And then 4 can go ahead and start in A. And notice that that's fine for the interleaving because nothing is in C. And so we move on to the next cycle. 2 is done. 3 moves on to the C unit. 4 moves on to the B unit. And we can't start anything in the C unit because 3 is in the C unit. Sorry, we can't start anything in the A unit. We can't start instruction 5 in the A unit because 3 is in the C unit, and we can only be using one of those at the same time, right? And because 3 is already in the pipeline, it has priority, right? You're not going to want to start another instruction if it's going to prevent a current instruction from executing. That doesn't really make any sense. You want to get through the instructions you've already started. Right, so then we move on to the next cycle. 3 goes ahead and moves on to the D unit. 4 moves on to the C unit. And we, again, can't start anything because the C unit is being used. So we go on to the next cycle. Finally, 4 goes ahead and moves on to the D unit. Now nothing is using memory, so we can start instruction 5 in the A unit. Whoops, I should put a 5 there. All right, so now next cycle. 5 then uses the C unit. Well, 4 is done here. 5 then uses the C unit, so it'll jump up here. Well, now there's still something using memory, so we can't start a new instruction. So we move on to the next cycle. 5 then progresses onto the D unit. Now nothing else is using memory, so we can go ahead and start 6 in the A unit. And then finally, in the next cycle, it'll move on to the B unit. So you see, like, sometimes earlier I've been drawing, it's like, oh, 1 uses all of these units, so I just draw it out. But that's not really what's happening, right? The CPU is figuring out exactly what needs to happen 1 cycle at a time, and all it knows is exactly what's going on in 1 cycle. And that's the process you should understand, is what's going on cycle by cycle. The CPU isn't really planning things out. Like, it doesn't just lay things out in the schedule and then see how everything fits. It does it cycle by cycle. It sees, I mean, if we knew how it was decoded and where it was decoded, then we would know exactly when dependencies would be handled or whatever. So you definitely want to be thinking about pipelines as a cycle by cycle thing. Any questions on this? Yeah, with the one-way interleaving, we can see that in every column, only at most one thing uses a memory unit, a unit that accesses the main memory. Okay. Let's clear that. Go on to number 14. So number 14 is one that has to do with dependencies. So here, A is just an instruction, doesn't have any dependencies on anything, so we're good. B accesses a different memory location and a different register, so that's fine. C takes R0, inverts it, and puts it into R2. So C execute here, and this pipeline is just the same like normal 5-stage pipeline that you're used to. So C uses the execute stage here because that's when it's going to not R0, and that's going to be dependent on the load for A, because that's when we actually get this value. Let me write this a little bit smaller. All right, so then we can go on to D. D uses R3, which hasn't been used before, so there's no dependency there. It uses R1, which is loaded here, so we do have that the execute for D depends on the load for B. And then we're overwriting R0. So we actually have a dependence between D and C here, in that the execute for D has to happen after the execute for C, which at this point it's not really worth noting, right? We know that instructions executes sequentially. We know that C has to go through the EX unit before D is going to go through the EX unit by just how the pipeline is defined, so we don't actually have to write this one down. But that is technically a dependency, right? We want to make sure that we're not overwriting R0 before it's used to do the not. All right, so that's D. E, we're using R2. So here we're going to be doing a store here. So the store for E depends on the execute for C, because that's when the value of R2 is used. And it also technically depends all the way up here on the load for A, but that's so far apart at this point that it's not going to be a problem. I mean, this is a 5-stage pipeline, so in the worst case, this is going to be in the store unit while this is getting fetched, which that's not going to, that like A is guaranteed to be done way before E reaches the store unit, so we don't have to actually mark down that dependency, because here we're reading from location 100, here we're writing to it. We want to make sure that happens in the right order. All right, so moving on to F. Here we're using R2, we're overwriting R2, and we're also using R0. So here the execute of F is going to depend on the execute of D, because that's when R0 is computed. And the execute of F is dependent on the store of E. Which is actually a dependency that can cause an issue, because the store unit is last and the execute unit is earlier, so it's probably worth marking this down, because here we're using R2 and we're storing it here, and here we're overwriting R2. So if we overwrite it before we store it, that's not going to be storing the right thing. So that is dependency there. And then finally on G, we have memory location 104. Here we read it, here we read it, and although they are super far apart, a read is not a dependency, right? If you read from the same location twice, there's no dependency. And we're overwriting R0, and so that means we do want to make sure that there's no dependency issue going on here. So the load for G is dependent on the execute for F, because we want to make sure that R0 is the correct value when we do this addition. So we can go ahead and draw out the schedule. This should be relatively straightforward because none of these instructions use all that many units. So the IF, ID, EX, or LD, EX, ST. So instruction 1 here is a load, so it's just going to use the LD unit. Right? It takes memory and puts it here. This is also just reading from memory into a register, so that's LD. C is just the EX stage. The add is just the EX stage. The store is just the ST stage. Add is just EX. And G is just the load. And this is not always true. This is just true in this example because we're either only doing a memory operation in the form of a load or a store, or we're doing register to register. So that's why it's LD, EX, and like none of them use more than one unit, apart from ID and IF, obviously. So we can go ahead and start figuring out how this stuff would be laid out. So 1 goes ahead and starts getting fetched. Once it's done, it can go ahead get decoded, and then it'll just move on straight to the load unit. And then it's done. So then instruction 2 would start here, get decoded here, and then loaded here. And I'm just sort of drawing this out arbitrarily because I know there's no dependencies, right? I'm going to look on this left-hand side, and if I'm working on instruction C, or instruction 2, or instruction 3, actually, then I want to pay attention to the dependencies and make sure that's satisfied. So 3 is going to get fetched, decoded, and then executed. And we can notice here that the execute of C, that happens right here, does in fact happen after the load of A, which happens right here. So that happens in the right order. So this dependency is good. It's satisfied. Then we have instruction D, instruction number 4. So that's going to get fetched, decoded, and then also executed. And here we have that the execute for D, which happens here, is dependent on the load for B, which happens here. Those happen in the right order, so everything's good. Then we have E, which is number 5, that will get stored. So we have 5, 5, and that jumps straight to the store unit here because there's nothing in front of it in the pipeline. And we do have that the store for E, which happens here, is dependent on the execute for C, which happens here. Those happen in the right order, so this is good. Then we have 6. So 6 gets fetched, decoded, and then executed. So here the execute of F, which is right here, depends on the execute of D, which happens here, and it also depends on the store for E, which happens here. That all happens in the right order, so both of these dependencies are satisfied. And then finally we have instruction G, which starts in IF, goes to the ID unit, and then just gets loaded. And we do have the dependency that the load for G happen after the execute for F. I should probably write that in the same way, execute for F. And the execute for F happens right here. Those happen in the right order, so everything's good. And it just turns out that none of these dependencies actually cause any issues. And this is our schedule. All right. So let's go and move on to the next question, unless someone has a question. Okay, so the next question is, you're making a memory component with a 32-bit data bus and 16-bit address bus out of 16-bit registers. So first of all, what is the size in bytes of the whole memory component? Well, if every address stores a full word, then we have 16 bits worth of words, right? So we have 16-bit address, right? That means that we have 2 to the power of 16 addresses, right? If each address stores a word, so we have 2 to the power of 16 addresses times, well, here a word is 32 bits, right, in the memory component. So 32 bits, that is 4 bytes, or 2 to the power of 2 bytes per address. right? Because every single address stores a full word. So, and a word is 2 to the power of 2 bytes. So that means the addresses cancel out, and we get a total of 2 to the power of 18 bytes, which is 256 kilobytes. Yeah. So our memory component here is 256 kilobytes in total. That's the answer to question A. So now we want to start designing this. So we have a 32-bit data bus, but we're only using 16-bit registers. So that means we're going to have to stack them horizontally in order to be able to fit everything in. So here I'm going to need I would have my data bus coming in, and I'm just going to sort of semi-roughly draw this out just so that you have an idea. And for like a test, we're not going to ask you to draw out the whole thing, because obviously that would be difficult, and even more difficult since everything's online. So you kind of just want to be able to sketch this out on paper somewhere. So this is going to be a 16-bit register. This is a 16-bit register. If I take the high 16 bits of this 32-bit number and the lower 16 bits of this number and I split it apart, I can connect their clocks up together somehow, and then it'll be acting like a 32-bit register. So 15 says 15B is asking how many columns of registers are there. Well, there's going to be 2 columns because we need 2 registers wide to be able to cover 32 bits. How many rows of registers are? So that means that we're going to have a whole bunch of registers. And keep in mind, the number of rows here is just the number of locations in the memory, the number of addresses. So we have a 16-bit address bus, right? So we have a 16-bit address bus coming in, which means we're going to have, and we're going to pass this into a binary decoder to do the decoding for us. And so this binary decoder is going to have 2 to the power 16 different outputs for every single possible 16-bit number, which is also how many rows you're going to have, because that's how many different locations there are. So there's going to be 2 to the 16 different many rows, right? Because we need 2 of these registers here per row to satisfy a whole number. And each of these, again, each row is one of the address in the memory. So we have 2 to the 16 of these, obviously too many to draw. Then you have how many total registers are there? Well, we have the width, which is 2, the height, number of rows, which is 2 to 16. So we have 2 to the 17 total registers is how many we're going to need to use. How many muxes are there going to be? So again, here we want to implement this out of registers, which means these registers constantly give an output, and so we need to control that output. So we're going to take these 6, the Q0 bit of this, of all of these, and we're going to pass this into 1 mux. Then we're going to take the Q1 output of all of these and pass them into another mux. And we're going to have one for every single bit, because we want to be able to choose the correct Q0 bit out of all the locations, the correct Q1 bit out of all the locations, the correct Q2 bit, and so on. For all of the different bits inside of this number, we want to choose the correct one from the correct location. And so the number of multiplexers we're going to have is just the number of bits in our data. So we have 32 muxes here, because we need one for the 0th bit, the 1st bit, the 2nd bit, all the way up to the 31st bit. Then we have how many variables are each of these muxes going to be? Well, that depends on how many addresses, right? How many inputs are we going to have into this mux here? Well, as many as we have locations. So we're going to have 2 to the power of 16 inputs into this mux, right? So this mux has to have 2 to the 16. So that means how many selector lines do there have to be? Well, there has to be 16, right? If you have 2 to the power of 16 options, you're going to need a mux with 16 variables so that you can have that 2 to the 16 options, right? Because remember, if you have a mux with a 3 variable input, 3 selector lines more specifically, then you're going to have 2 to the 3 inputs. So if I have 16 lines, I'm going to have 2 to 16 inputs, which is what I have. So we're going to have 16 var muxes. So 32 32 total muxes, each of them being 16 variables. Then how many tri-state buffers are there? Well, if you remember from how you draw this out, every single multiplexer here is going to be connected into a tri-state buffer, because that's how we control whether or not that we're actually producing an output. The tri-state buffers, again, sort of like cut the wire. And so if the input to these tri-state buffers is 0, we're not going to be outputting. If it's 1, we're outputting. And so we need to put one of those on for each of the multiplexers for each of the bits in the output to prevent each individual bit from being output. And so we're also going to need 32 tri-state buffers. And I sort of went through this quickly, but this is the sort of thing where you want to go back, watch videos on memory systems here and how to construct them. And you want to know how to construct them, right? The only way you're going to be able to answer these questions is if you know how this sort of thing works and how you'd be able to draw them. I'm sort of just sketching it out because drawing it in full is complex, but yeah. Any last questions on this? Okay. So next we have something dealing with memory. So we have these three instructions. So we have move R1 12 R0, which we want. So the comment over here is telling us what we want it to do. So we want it to do R1 equals not Y. Then we have and R1 V1 R0. Here V1 is just it's a variable, right? There would actually be a number here, and it's invalid to put anything else but a number, but this is just a placeholder. And the question is asking, what do we have to put this here to make everything work? So here we want this to do R1 equals R1 and Z. And then finally we want to just do X equals R1. So here we'll be putting it back into main memory. So that's mov v2 R0 R1. So this is really just talking about how memory manipulation works. This is exactly talking about the concepts that you used in the memory VML stuff. So and additionally the problem does state that X is at location 128, Y is at location 196, and Z is at location 228. And we also know that Y has the value of 6, Z has the value of 2. Okay, so sorry, this should not be not here. This should just be Y. That's my bad. When I changed the problem, I didn't change that. There we go. So here I'm just going to take Y and put it onto R1. So if I want this to point to Y, then I need 12 bracket R0 to reference location 196 in the main memory. Well, we know how this works. We take 12 and add it to the value of R0. So we know that 12 plus whatever R0 is equal to 196. So that means R0 is what? Well, we can just subtract 12 on both sides, and we get that R0 equals 184. So you know here that at the beginning of our code, if we look at our registers, we have R0 is 184. Right, because we want this to be pointing to location Y, and so R0 has to be 184, so that 184 plus 12 is 196. Okay, and then what we're doing with this operation here is we're taking the value of Y, which is 6, right? The value of Y is 6, Y is at 196, and we're putting it into R1. So R1 is now going to hold the value 6. Then we're going to AND that. We're going to take R1 and AND that with whatever Z is. Well, Z is, we want this V1 bracket R0 to reference the location 228. Well, we know that when we were referencing this, it's just going to be whatever V1 is plus the value of R0, but we know the value of R0. The value of R0 is 184. Right, and we want this to equal 228. So that means V1 equals 228 minus 184, which is just 44. So that means V1 is 44. Yeah. So R0 is 184, and I'll write V1 is 44. So here, if we want this to do R1 equals R1 and Z, we should be putting, this should actually be a 44 here. That's what we're saying. Okay. And also this operation is going to be doing the bitwise AND between R1 and the value of Z. So the value of Z here is 2. R1 is 6, so we don't really need to represent more bits than this. So that's 6. This is 2. If we do bitwise AND, 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 0 and 0 is 0. And so we end up with this. And I mean, obviously, there would just be more zeros here, depending on how many bits there are. And so that means that the result is going to be 2. So 2 and 6 is 2. All right, and then we have this last operation here. So now we want to take the value of R1 and put it in X, right? So that means we want V2 R0 to point to X. We want that to resolve to the location of X, which is 128. So that means we want V2 plus R0, which is 184, to be equal to 128. So now we're going to end up with a negative number here, but that's fine. There's no problem there. So here if I do, let's see, we have negative V2 is equal to 184, 184 minus 128. Just to make it simple, so we have 184 minus 128. So that's 56. So V2, so we have negative V2 equals 56, or V2 equals negative 56. And so V2 here should be negative 56. And yes, it's perfectly fine for this value to be negative, right? Because negative numbers just work like any other number when you're dealing with 2's complement. And so that's the answer. So V1 should be 44, V2 should be negative 56, and R0 starts at 184. Note how, in order to be able to figure out V1 and V2, you actually needed to figure out R0 first. So I mean, if you come across this sort of question, you just make sure you're thinking about how things work with the memory, what order things update in, all that sort of stuff. Okay, so next question is, we have a computer with a 16-bit data bus and also a 16-bit address bus. So we have data and address. And we are putting in these blocks here. So we're going to be implementing a memory structure with blocks that have an 8-bit data bus, so 8-bit here, and then a 12-bit address bus. How can we go ahead and implement this? Well, we can't just have one, because if we had only one of these units, then that would only store 8 bits. But we want to be able to store 16 bits, right? If we want this computer to still be functional, we absolutely have to satisfy the data bits, right? It makes no sense for a computer to be 16 bits, yet only store 8 bits of those numbers, right? That wouldn't be a 16-bit computer then. So in order for this to still be functional, we're going to have to use 2 of these in order to be able to store 16 total bits, right? And then we connect these address subs together, right? And if we do this, and let's say we take the upper 4 bits and then the lower 12 bits, and we just take the lower 12 bits and wire them directly up, and then we just ignore the lower 4 bits, this technically would still work. The computer would still function. It would just have a bit less memory than amount of addresses that it could address, right? It's just wasting some of the address, but that's fine. The computer will still work. And so here we have 2 of these units. Well, first let's figure out how big this unit is, right? So we have 2 to the power of 12 addresses, and at each address we have one 8-bit number. Well, one 8-bit number is just 1 byte, so we have 2 to the power of 12 bytes, right? Which is 4 megabytes. So one of these units here is 4 megabytes. We have 4 megabytes here as well. Well, we have to use 2 of these units to satisfy the data bus, and so the minimum amount of memory is 8 megabytes, because we have to use 2 of these to make the minimum, to at least satisfy the data bus. So now if we want the maximum, well, the maximum, I mean, just keep adding units here until your address bus gets run. Like, it's just fill out the whole memory, right? Well, how big is that going to be? Well, we don't even have to fill it out. We can just look at the data bus and the address bus, right? Assuming that, like, you want to definitely want to look at this and make sure that you'd actually would be able to tile enough of these to completely satisfy this. But if you are able to fully satisfy the 16-bit data bus and 16-bit address bus, then you're going to end up with a memory component that has 16-bit data and 16-bit address, which means it's going to have 2 to the power of 16 locations with 16 bits is 2 bytes, so times 2 to the power of 1 bytes per location, which in total is 2 to the 17 bytes. Or in other words, let's see, 2 to the 7 is 128? Yeah, which is 128 kilobytes. Sorry, this is not megabytes, that's kilobytes. 10 is kilo. Right, so and then here, 2 to the 17, that's 2 to the 7, which is 128, times 2 to the 10, which is our kilo bytes. So the maximum here is going to be 128 kilobytes. Because, I mean, if we make a component with this, we just end up with 16 bits of data, 16 bits of address, and so we know how many bytes there are. Right? It doesn't really matter how these are laid out. And then finally, how many bits of the addressing coming from the computer would need to be decoded, right? So the lower 12 bits are going to just go into all of the sets of blocks directly to address within the blocks. And then the rest of the bits, which is 4, are going to need to be decoded in order to select which set of blocks we're actually going to be writing to. So here the answer is 16 bits is 2 bytes, which is 2 to the 1 bytes. Right, we want to represent our answers in bytes, not bits. So 16 is not 2 to the 4 bytes. It's 16 is 2 bytes, which is 2 to the 1 bytes. Okay. Any other questions on this question? And yeah, so just to write it down, C is 4 bits, right? Lower 12 bits just go directly into the components. Upper 4 bits get decoded to select which set of blocks here. All right, and then last 2 questions here. So the first one is just a normal cache question. So I'm going to start off, I'll say my system here. That's just my computer. It's a 16-bit computer, so it has 16-bit data. And then we have 128 megabytes of main memory. Right, main memory. So if we want to figure out how many bytes there are in this and how big the address is going to be, so that 128 is 2 to the 7, M is 2 to the 20 bytes, so we have 2 to the 27 bytes. Okay, which means our address is 2 to 27. All right, again, I do this, you want to do this as you're reading it, right? Don't miss any information. Right, I've only gotten what 1, 2, 3, 4, 5 words in, or maybe 8 if you're counting the of main memory. Read it, write down what you know based off of what it's told you, and then keep moving. So then we have is upgraded with a 128 kilobyte 4-way set associative cache. So we have our cache that is 128 kilobytes, which we should write as 2 to the power of 17 bytes. Right, 128 is 2 to the 7, kilo is 2 to the 10, and it's 4-way set associative, or I'll write 2 to the 2-way set associative. And that's all the information. And then we have each line is 32 bytes, so one line equals 32 bytes. Let's go ahead and just convert that straight to words. So one word right? So 16-bit data is also just 2 bytes, right? Just divide by 8. So if 2 bytes is 1 word and 1 line is 32 bytes, that means 1 line is 16 words. Right? If you just pair up every adjacent 2 bytes in 32, right? So you have 32 things, right? And you just take these two, that's 1 word, that's 1 word, that's 1 word. You're just dividing by 2. So 1 line is 16 words. And then we want to figure out the tag, index, word, and byte portions of the address. So tag, index, word, and byte. All right, so the byte portion is how many bits do we need to address a byte within a word, right? We have 2 to the power of 1 bytes within a word, so we need 1 bit to address a byte within a word. The word portion, how many bits do we need to address a word within a line? So a line is 16 words, which is 2 to the power of 4 words. So we need 4 bits to address a word within a byte, or within a line. Index, we now want to compute the width of the cache. So our cache, well, we have 1 set per index. That's always true. Times, well, we have 4-way set associative. So that means we're going to have 4, or I'll write it as power 2. So 2 to the power of 2 lines per set, right? That's what this tells you. Times, well, how many bytes are there? Like, we could use the word per line and then bytes per word, but we already have bytes per line. So we can just do 2 to the power of 5, which is 32 bytes per line. Right? You might ask, why did I do it in this order? Well, set cancels out with set, line cancels out with line, and I get bytes per index, which is exactly what the width is. It's always bytes per index every single time. Look at the units. If the units don't make sense, if they don't work out, then you're doing it wrong. The units should always make sense. So here we have 2 to the power of 2 times 2 to the power of 5 bytes per index, which is 2 to the power of 7 bytes per index. All right, so actually, let me do this to the side here. So now we have just our normal rectangle math. So we have 2 to the 7 bytes per index is our width. Our area for the cache is just the number of bytes in it, which is 2 to the 17. And so indexes here has to just be 2 to the 17 divided by 2 to the 7, which is going to be 2 to the 10 indexes. So we have 2 to the power of 10 indexes, which means our index portion here is going to be 10. And then we know that our address is 27 bits total. So this all has to add up to 27. So this is just going to be whatever's left over. So if I do 27 minus 10, that's 17. Minus 4, that's 13. Minus 1 is 12. That means our tag has to be 12 here. Right, and then we can just check going 12 plus 10, 22, plus 4, 26, plus 1, 27. 27 bits. All right. And then lastly, we have the reference matrix. We'll get through this quickly, and then there'll be the rest of the time just for any random questions people have. So now we have, we're doing reference matrices. So we have 3, 5, 3, 10, 11, 5, 6, 11. So this is what we're accessing, the tags that we're accessing. And these are all being accessed at the same index, so they're all being accessed in the same reference matrix. So we're going to start off with a blank reference matrix, which is just essentially all ones, and that just means that nothing's the oldest. So here, the oldest, we're looking for zeros across, ones up. I usually like to write this down so that you don't forget. Oldest, zeros across, ones up. Set newest is the opposite. It's ones across, zeros up. Okay, so here the oldest we know is 0. And then I'll also want to draw my actual set here. So my set has, it's 3-way, this is a 3-way set associative cache, so that means there's 3 locations in the set, locations 0, 1, and 2. So 0 is the oldest. We access tag number 3. 3 is not in our set, so that means it's a miss. There's no difference here. There's 0, 1, 2. It's the same exact thing as just doing 1, 2, 0, 1. Yeah, it's just cutting off rows. This is just a grid here. There's absolutely no difference between these two. Right? 0, 1 is that square. This square is this square. And this square is this square. There's no difference. So it doesn't matter how it's laid out. What matters is where the intersection of the columns is. So here, 0, 1, 2, 1 column, and so on. So 3 is a miss here because it's not in the cache. Then we have 0, 1, 2. So because 3 is a miss, we look at the oldest, we put it in the oldest position, and then we update the reference matrix. So because we just put something in location 0, we're going to put 1s across and 0s up and leave everything else the same. So then the oldest here is then going to be 1 because 1 has 0s across and 1s vertically. Then we go ahead and access 5. 5 isn't in our set, so it's a miss. Because it's a miss, we're going to put it in the oldest position, which is right here. And then we'll update our reference matrix. And we'll do that by putting 1s across here, 0s up, and then leaving everything else the same. So now here the oldest is 2. Right? And I'm not doing that by looking at the history. The whole point of the reference matrix is you can tell what the oldest is based off of the reference matrix at one point in time. So here I can see that 2 has 0s across and 1's up. Right? There's nothing in the 2's column, so it always has 1's up. It always has 0s up. Doesn't matter. There's nothing there. So the oldest here is 2. Then we access location number 3. 3 is a hit. If we look in our set, 3 is there. So that's a hit. And so we're going to update wherever 3 is. 3 is in location 0. So we're going to update location 0. So for that, we're going to put 1s across in the 0 row, which there's nothing there. And we'll put 0s up here. So we end up with this. So now the oldest is still 2. Because, right, 2 has 0s across and nothing up. Then we access, let's see, 10. So 10 is not in our set, in any of the sets, so it's a miss. And we'll go ahead and put it in the oldest position. So that's 2. And then we update the reference matrix. So because we just put it in 2, we're going to put 1s across and 0s vertically. There's nothing again vertically, so we'll do this. And then if we look at the oldest is now 1. Then we access 11. 11 is not in the set. That's a miss. So we're going to put it in the oldest. So we're going to overwrite 5 and put it there. All right, so that because we put it in location 1, we're going to put 1s across and 0s up there. So we end up with this. And now our oldest is 0 again. So here we're accessing 5. 5 is not in the cache because we just replaced it, unfortunately. So this is going to be a miss, and we're going to put it in location 0. And we're going to update location 0 in the reference matrix. So that means we put 1s across, 0s up, 0 here. And so the oldest is just going to be 2 now. We then access 6. 6 is not in the cache, so that's a miss. So we'll go ahead and overwrite the oldest. So that's right here. We'll put 6 there. Then we have our reference matrix. We update 2, so we put 1s across, leave everything else as is. And now our oldest is 1, right? 0's across, 1's up. Finally, we access 11. 11 is a hit. It is in the cache. So this is going to be a hit. And as a result, we're just going to update reference location number 1. And that is going to be putting 1s across, 0s up, leaving everything else as is. And this would be, the oldest now would be 0. But that doesn't really matter for this. Any other questions on this question here, specifically?